for this campaign was to study biogenic emissions in Australia, in Southeast Australia. So we called it the COALA campaign. In fact, we changed it to call it COALA 2020 because we haven't entirely given up hope that maybe one day this will happen. But it's certainly, this COALA is having a big nap. It's in hiatus at the moment. But lots and lots of people involved, and yeah, it was based in effectively like halfway between Wollongong and Sydney. We did it in an area, originally thought we're going to have a lot more instruments there, so we were looking for somewhere with a lot of power, and we wanted an open forest because there'd been some measurements suggesting that if you were in a deep, dense forest, that the isoprene is mainly emitted by the canopy, so you wouldn't get that, and we're going to be on the ground. So we found a site at Cataract Scout Camp, which is scout camps. You wouldn't, I would kind of think of scouts as just like intense and, you know, having bonfires and things. I don't know why they need a lot of power, but wow, they had like, you know, 4 different panels of power in each campsite. I think like 4 plugs of 3-phase power, as well as 15 amps. So there was plenty of what we needed. I think I can remember roughly. I think that I'll start off by just flicking through. As I was saying, this was not. Yeah. I know. Okay. The campaign was COALA, characterising organics and aerosol loading in Australia. It was a campaign that was all about biogenic emissions. It was not meant to be about fire and smoke. I'd left that behind, I'd moved on, wanted something new to play with, and I timed this campaign for the middle of the Black Summer bushfires. So what we got was a campaign that had quite a bit of smoke. Page now?
This one?
Okay, cool. So yeah, it's basically, I've kind of talked about where it was. So the lovely Wollongong, which I suggest everyone visits because it's lovely, is here. Sydney up here, this large area of natural, it's got a eucalypt forest, and here was our site. And we had basically a little soil sampling campaign. We had an air quality monitoring station, some filters from the guys from Nagoya University, Airbox, which is a mobile lab that's a shared facility for the Australian community, and Georgia Tech sent Peter Armis off and a PhD student who helped run it. I'm just going to flick through to some photographs of the site. And some of the teams, there's Melita actually yielding a spanner, so you know she does actually get her hands dirty occasionally. Setting up the tall tower that we measured Peter Armis through. A bunch of the things that we measured. But here we're all about smoke. This is an image from Himawari of the widespread fires and smoke on the 3rd of February. This was pretty much the last kind of major smoke day. But as you can see, we're kind of in here in the middle of all those fires. And one of the issues, and the reason I want you to see this, is that, you know, we were measuring age smoke. We were sitting there for about 2.5 months and just surrounded by fires. I think Susan was there at the time. And yeah, the fires were burning everywhere but to the east, and they would have been burning to the east if there wasn't an ocean there, I'm pretty sure. So everything was on fire. So this is like a plot of the whole campaign, starting from mid-January, early January. Carbon monoxide plotted on the top, and just a particle number on the bottom. And what you can see when you look at the carbon monoxide at the top, we've got some kind of smoke events that are coloured in red, and you can just see that the size of all this sort of peak CO was really large at the top of at the beginning of the campaign, and then the later part of the campaign, we didn't see as much CO, but in the later part of the campaign, we're starting to see some of these really large peaks in number concentration. And the point being that all the new particle formation, which was what we were trying to see, was completely suppressed in the smoke period. So basically there were so many particles in the atmosphere, they didn't need any new ones, they just coagulated onto what was there already. So just saying, like, yeah, we had an unexpected research opportunity. It wasn't what we were after, but we had an opportunistic new research focus. So we wanted to look at the composition of the aged smoke plumes, and actually flipping this talk, not to talk about chemistry because I don't have a nice aircraft, so all I can see is what it looked like at an age that we're not really sure we can determine because there are all those fires that we're just sitting in the soup of it. But what I was interested in was kind of thinking about the relative toxicological contribution of the smoke plumes. So here we are, here's an image of where we are and some of the more fires. This time we're looking at January the 30th, and you can see again, we've got quite a lot of smoke around. And we're looking at the time when we've got smoke and we've not got smoke, and again the CO, and this time the PM2.5, and just seeing the kind of range of concentrations we were seeing in the smoke compared to when it was clear. So, you know, when we were trying to look at the smoke composition, we're basically just looking at enhancement ratios to carbon monoxide, and we're seeing a bunch of different compounds that we could see here. The top lot is in the gas phase, so we've got acetaldehyde, acetonitrile, benzene, and we've also got methane, methanol, and then in the particulate phase, ammonium, we've got nitrates, organics, and all of these we can kind of get a good idea about what we're looking at in terms of the total composition. And my point being that all of these different things that might have a toxicological load for humans are all really well correlated to carbon monoxide. So it's a little bit simplistic because of the aging, but we can kind of use this as to get an idea of what you might be being exposed to. So now for something completely different, we can think about toxicological classes, and there are a whole bunch of them, but you can see I've skipped a few numbers here. But basically they're ones that we tend to come out worse when we start looking at this for smoke is the first 4 eye disorders, which is basically that people, you know, smoke makes your eyes run, it's a problem. Upper and lower respiratory problems, disruption of oxygen transport, of course that's carbon monoxide, and finally a little bit of skin problems and the carcinogens at the bottom. And what I've done here is take a whole bunch of the typical gases and things that we see in smoke and assign them to which toxicological class they're active in. As you can see, which of the gases that will be worse for exposure to smoke depends on a couple of things. What the typical concentrations we see in the smoke and their toxicity in these different classes. But of course in smoke you're not just being exposed to one of these. You've got a whole gambit, whole mix, and they all combine together. So we don't really know what it means, and I don't suppose you get ethics to put somebody into a smoke chamber and expose them to all of this stuff. But basically our first guess is that it's not one thing or another, that there will be cumulative. So this basic guess is that we think the total effect, you're going to at least sum up the effect for the different gases if they're attacking the same, in the same toxicological class. So this is a very basic equation that's basically saying that the total exposure effect should be considered to be the concentration of gas 1 over the safe level that's in your legislature. And then you add up all the different gases compared to their safe limit if they're in the same toxicological class. And then looking at some of the smoke events that we had at Cataract, and just considering the chemical soup that we were breathing in while we were there, we can break it down, as I say, into these different classes that I told you, and see all the different gases that were of most concern and the particulates. There is nothing that we have, because we don't have standards, safe work standards for any kind of chemistry within the particulates. So the particulates are just lumped together as if that was the same thing, whether you're breathing in sea salt or toxic metals or anything. But what you can see here, really, it's half of the toxic load on your body is coming from the particles. But formaldehyde is also quite bad, and acrolein is another one that's pretty bad. Unfortunately, we didn't measure HCN in this particular campaign, but that's another one, hydrogen cyanide, that's got quite high concentrations in smoke, and is also, no surprise, not particularly good for you. So we can then take that same setup and think, well, what does that mean to the good citizens of Australia, or the bad ones for that matter? Here we have in Canberra, we had like the worst air. We beat Delhi. I know there's quite a few people who have been telling us how bad the air quality is in Delhi for a few weeks. Like, there were quite a few Australian cities that managed to do worse. Canberra had the worst air quality in the world for about 2 or 3 weeks, certainly across this first couple of weeks of January, showing PM 2.5 measured in Canberra at the top and carbon monoxide at the bottom, and also plotted the kind of daily concentration limits that are set by the Australian government. So assuming then that we've got the same age smoke sitting in Canberra than what we measured in Canberra, what would that mean? And again, this is just broken down into some different events, and looking at, you can sort of see the very worst pollution was on the 1st of January, and you can see that the gases now they actually have a larger toxicological impact than the particulates, which is always the focus. So really just concluding which of the gases are of worst concern, it kind of carbon monoxide, formaldehyde, acrolein, sulfur dioxide and acetic acid, also hydrogen cyanide. They're all kind of mainly attacking the upper and lower respiratory tract, eye irritation, disruption of oxygen transport, and also carcinogens. What about PM 2.5? Also problems in these same classes 1, 2, and 3, which is the eye disorders and the respiratory tract, the skin problems, and carcinogens. They're what all the focus is for human health. They are bad. They are the single worst thing toxicologically, but they're not as bad as all the gases put together, and that's just the ones we can measure. So I guess my final kind of summary of this is, we should be thinking, but beyond the PM 2.5 to all the other things that are not very good for us in smoke. Okay, so Adik gave me these slides, and I was thinking, it could be complicated, but Hugh has just explained quite a bit of this to you. So this is basically looking at the event in the particulate phase. So we've got a TOF ACSM in that airbox, and we measured the biomass burning organic aerosols. At COALA, he also looked at Canahook, Cape Grim, which is the Gore clean station down the bottom of Tasmania. So what we're seeing is basically the fire counts in the region for the smoky period in COALA, the clean period in COALA. I forgot to say that after that first image I showed you of the fires and the smoke from Himawari on the 3rd of February, we had like a once in 3 decade rain event that absolutely cleared out the air, and so we did actually get some cleaner period. And this is the hotspots around for the whole of the time we looked at the Cape Grim record. So he's basically looking at the measurements for the 2, and looking at the total number of hotspots for the times, the fire rated power integrated over the whole areas, and the distance that the kind of smoke we like to see up is. And you can see that in this clear period, there's not really a lot of smoke there anyway, so I'm going to mainly ignore that, but you can see that we are much closer to the smoke than the COALA study, typically about kind of 8 hours aged. And in the Cape Grim stuff, you're talking about fires more like 500 kilometres away. So I repeated the plots from the first thing, and so I want you to look at the middle panel now, and you can see the total organic concentrations. You probably can't, but you're looking at around the kind of 30 micrograms per cubic metre in COALA. COALA clear stuff, pretty much nothing, and at Cape Grim you're probably around the WHO standards, about 8 micrograms per cubic metre, just in the organic fraction. And then, as explained by Hugh, we're looking at the different fractions. So we've got the fraction of oxygen OA. There should be another plot here, I think. In the middle panel, and you can see this is the aged aerosol at that time, and you can see effectively that we are relatively aged. And the COALA smoky bit, the clear bit not so much so, and much more aged because of this the fraction of OA. It's the 44. And then we've got the biomass burning aerosol. So this is the I thought I had another plot of it, but this is the 44 to 60, the lead glucosan to the 44. And what else do I want to say here? Basically, this coagulation, you can see that this enhancement ratio of the organic aerosol related to the fire related to the fire relative power. So I'm being a bit unclear about this. I put a Deep's email address there. He's also got a poster that we've put in, I think it's poster 16. So, and he invited people to email him because he's about to get on a plane to Indonesia. That's all I have.
Thank you. Thank you very much for a great talk. So I guess we have questions first from John.
Okay, comment/question now. In your effort to characterize the biogenic aerosols, I know you have this smoke influence, but do you have like some regional dust transport events influencing your effort to characterize biogenic aerosols as well?
Yes and no. So we did get I think 1 or 2 big smoke events. So we had like a big, a really windy day with westerly winds that brought, it intensified the fires that were burning to the west, but it also brought dust. So we had an event that was dust and smoke. Most of the time, we didn't have a lot of dust. And in Australia, you don't. It's kind of the land of extremes. We don't get a lot of dust until we do, and then it's like massive. So we get these big kind of events with a background of very low dust.
Yeah, thanks, Claire. I have kind of like a morbid question, but because of the combined effects that are expected, has you or anyone looked at that health data, maybe lagging a bit, like to see if there was a corresponding spike in, I don't know, deaths or diseases or something?
It's quite difficult. There is a kind of cohort study in Sydney called the 45 and up, but it's really difficult to, you can look at these big smoke events and look at the hospital, the hospital data for people coming in for cardiovascular problems, and that's clear. But in terms of the longer term exposure, no, it's really difficult. And yeah, I'm not an epidemiologist, so I don't fancy getting into that. I mean, I like to be a I like to be broad in my interests, but maybe not that broad. But I mean, so a lot of our interest in the toxicology is partly, you know, I have a bee in my bonnet about the about PM 2.5 and how it's just like PM 2.5 is the be all and end all. Very few people are talking about the actual chemical composition when we're thinking about health. And, you know, on the fireground, so one of the project I've got that Max is working on is like we're looking, part of the thing is to think about firefighter exposure at the ground, you know, and then you're looking at seriously large concentrations and then like giving them uncomfortable masks to wear that don't actually stop things like acrolein and hydrogen cyanide and formaldehyde getting through to their lungs. So, yeah, it's what we're interested in more.
We have another question from Hugh.
Well, it's just to follow up on the hydrogen cyanide thing, really. I wondered whether I know you didn't measure it,
I raised that because we measure it when we do open path FGS, so we've got a pretty good idea about what the hydrogen cyanide emissions are from nuclear phosphates.
Well, I just wondered I was just going to say, if you used emission ratios to come up with an estimate of HCN, what sort of size of a contribution to the toxicity do you get? So just to give you, just as an idea, really.
Yeah, kind of like in between, like what we get for formaldehyde. Formaldehyde is still largest, but yeah, up there with acrolein, it's a big one.
Steph.
I was curious, maybe just to clarify, the second site that was further away, was that also measuring the trace gases?
So yeah, I was ill prepared for this talk completely, and then the deep was like, oh, you should show some of my slides, and I thought that when I looked at them, I thought there was a nice thing that was showing the F44 and the 60, the levoglukosone and the ox, and yeah, so but the stuff that I was showing was from Cape Grim, so effectively that's a clean air site.
Right.
So it's designed to pick up Southern Ocean air and to study what's happening in the clean Southern Ocean. But the wind doesn't always blow from there. Sometimes you get like fire impact. So he ran the ACSM there for 2 years and he was looking at the data and he was like, oh, I'll pick out the fire stuff because he started with the COALA data set. And so yeah, it was a contrast of the two. But I'll probably be even more incoherent about his paper. So I might get you to go and look at the poster and email him, or I'll catch up with him.
Yeah, that's good. I mean, I guess I was trying to relate maybe what Hugh was saying about as the plumes are diluting, you're getting the partitioning of the VOCs off the particulate matter, and then you're getting the oxidation and the fragmentation of VOCs, then maybe there's more of a downwind production of some of these gases, like formaldehyde, for example, and if you had measurements.
So the formaldehyde thing is really interesting. I'm really interested in that because you can see it from space. And I was trying actually, earlier on, I was trying to see if I can find some images because I've been talking to Louisa about this. And I think, because the formaldehyde grows in, you can see it from Skiamarki oil. There was a big, you can see it from Chopami, you can see it. Yeah. And I think that basically pretty much every VOC that's emitted by the fires is going to chemically oxidize and produce some formaldehyde at some point. I'm talking as if I'm a chemist, which I'm not, but you know, I hang around people who know about this stuff. And so you can see, when you see some of these big satellite images of the formaldehyde from space, it's not at its strongest over the fire or the day of the fires. It's about 24 hours later was when you get peak formaldehyde. So I just think it would be a really interesting thing to, and you know, if you know someone who's a really good modeler like Louisa, maybe we could look at the total, you know, you think, all right, so it's going to, in what, about 3-hour photochemical lifetime when it's sunny. I don't really know what the lifetime is once it gets dark, but a box model of the MCM might be able to tell you that. And then you look at, with the satellite images, what it looks like at the fires the day after, and kind of, you could maybe backtrack it to a total VOC loading from the fires. would be a fun thing to do. And an excuse for Louise to come visit me in Wollongong. It's still a nice place.
Thank you, Claire. I have a question now. You showed in one of your slides, like you separate the aged plume and fresh plume, and there is a live event where you observed very large particles, which is related to burning. Right? If I catch it correctly.
So very large concentrations of particles, yeah.
I mean, the coarse particles, large size particles related to burning. So I'm just wondering, is that related to the vegetation type? For example, if you have bushfires, you would like to expect the mix of dust from the soil or something, or?
Yeah, I mean, I don't really know because I think we didn't measure them. There were some PM10 measurements, but I didn't look at large amounts of the we have an SNPS and we've got some measurements of that. There was certainly some large fraction, like there were some large particles in these smoke plumes. Susan can probably attest, you could be sitting outside and having your dinner and there would be like leaves dropping down into your pizza. So there was a lot of soot and a lot of the fires were spotting fires from leaf matter. So, but yeah, I haven't looked into that in any great detail.
Yeah, thank you very much. Okay, let's thank you for Claire again for the great talk.